Welcome to day 2 of the 100-day FPGA series. In the last video, we implemented a buffer and used a switch as the input method and LED to see the output of the buffer. In this video, we are going to be writing Verilog code for all the basic logic gates, and today we will also verify it using a test bench. So testbench verification in Vivado will also be covered in this video itself. Okay, and in the coming videos, we will also verify everything on the test bench. So starting off, let's fire up our Vivado. So you already know the flow. Go into create project. Again, I will be using Nexus board, so I'm going to boards and selecting Nexus. In the last video, I had explained about the part number. Every board has some part number that you can input here and select it, and you can also download the board files that I have explained in the last video. So here just click finish. Starting off, we will first create the sources. So first we will have our design source. So in the design source, go into next and create a file. We need to design Verilog code for implementing these logic gates, right? So most of these gates have two inputs. The basic ones, you have multiple input AND gates as well, but for here you will just make two input AND gates. Only NOT has one input AND gate. So let's think of how we can design it. Declare two input switches, let's say A and B, two input ports, and we can output let's say Y. Okay, let's first implement just single logic gate. So let's implement AND gate here. In Verilog, you can just write assign Y equals to A and B. This is one method of doing it, and this is called Dataflow method. We are defining how the data interacts. So we have just written the expression here, right? This will implement an AND gate. Now if you want, you can also do and write the output here and followed by the inputs, any number of inputs you have. This will also do the same thing, and since AND gate is actually native, so you do not need to write an instance name here. Usually when you call a module, you need to give an instance name here. So here you do not need to give, because AND is a native logic gate. So right along the process, we are also learning Verilog, right? So this is another method. So these are the mainly two methods here. I'll stick with Dataflow because in simple designs you just better to write Dataflow expressions here. So this is AND gate. We have finished here. So the next process after designing, the next process is let's first synthesize this code and see what we are generating here. Okay, so as you can see, the synthesis is completed. We can see the design that it has generated, the circuit that it has generated by going in here and choosing schematic. Now here we expect to see an AND gate, but let's see what we get. As you can see, we have two input ports here. So we have port A and port B, and these are just connected to a buffer from the pin inside the FPGA. The data goes from here to here and it goes into an LUT. Now you expected to see an AND gate, and you are seeing an LUT here. Let's first actually see what the RTL analysis shows. So in the flow navigator, you have RTL analysis tool, and here if you open the schematic, let's see what we see there. Now this is the RTL schematic, RTL analysis schematic, and here you can clearly see it is RTL AND gate, right? So this actually is an AND gate, but when we synthesized it, it got into an LUT, right? So we saw an LUT. So this is the way in which a circuit is implemented on an FPGA. So for understanding why this has happened, you have to understand the architecture of FPGA. In FPGA, you do not have AND gate, OR gate, and these are connected. No. In FPGAs, you have configurable logic blocks, right? Configurable logic blocks and interconnects between them. And most of the constituents of the configurable logic blocks have LUTs, that is lookup tables. Lookup tables basically map your input to your output. this is the something I'm going to make a video, separate video about the architecture of an FPGA, where you will be able to understand it in detail. But just understand for now, just understand that this lookup table over here is basically mapping the behavior of an AND gate, and since this lookup table is already present inside the FPGA, it is implemented in that way, right? AND gate is not present like inside, lookup tables are present inside. Okay, so this is why we see a lookup table. But in the RTL analysis we saw that the RTL that we are giving, the code that we are giving, the Verilog that we have written is actually generating a AND gate, and this is how it is being synthesized inside an FPGA. Now we will do the implementation, and for doing implementation, what's the first step? The first step is the declaration of the pins, right? Declaration of the pins is done by giving pin constraints, right? Go into sources and just add another file where we will write the constraints. So add or create constraints, you go to next, just give any name and just go finish. Now you can just close the synthesis design. This is an empty constraint, and I have explained how you have to fill the constraints in the previous videos. Okay, so in the last video I had explained how you can add master XDC files. Okay, now we will take the inputs and output that pins that we require from the master XDC file. So you can see this is the master XDC file. We need two of the inputs, right? We have declared A and B, so let's set those two inputs as the two switches, slide switches. Okay, you can also set it to buttons as well. So if your master XDC file has a button, here you can take the buttons as well for the input. Okay, right now I'm just taking the switches. So first two switches I'll put it here, and don't forget to change the name here. Okay, you have to set the name the same that you have set it in the RTL. So A and B, and the output is LED, right? Just one output, so one LED we need to copy and save it. Okay, now we can run the implementation. Now before running the implementation, actually since I told you that I will do the test bench verification, let's do the test bench verification first. Okay, let's verify that our design is working properly or not. So for so we'll pause this here. Let's go into simulation environment. So this is how you do simulation in Vivado. Let's see how we do. You just go into add sources, go into add create simulation sources. Now in the simulation sources, you just create a file and just write. This is the convention that we use. Just give the name of the file DUT, design under test, and write underscore TB. Okay, and you do okay, and here you create the file and just hit yes. Now in under the simulation sources, you will see your test bench created. Go into your test bench and expand this here. Now a test bench does not have an input and output, since we have test bench is the environment itself. We are providing signals to the design sources, right? So the first thing that you do inside a test bench is to instantiate the DUT, design under test. Design under test in our case is logicgate.v, that we need to test, right? This is the design that we have created and we need to test it. So we need to create an instance of this. In Verilog, how do you create an instance? You basically have to write this thing. First, the instance format is you write the module name. This is the module name. As you can see, you write the module name and you write the instance name. Right here the instance name I'll put is DUT, design under test. Okay, now the format here is actually there are two methods of giving the inputs and output mapping, as you might know. First way is to specify the inputs, something like this. You have an input A, input B, and an output C. So this dot operator actually is like mapping your signals into the actual port names. Okay, so we need to declare the signals here that we will provide into the DUT. Inputs in the test bench we will add reg. Okay, since we need to modify these inputs inside an initial block. Okay, this is the format. The inputs are named in reg and outputs in wire. Okay, now just go into these and just provide the names of the signals. Now you can write different signal names here. For the sake of simplicity, I have kept the same name, and now the DUT instantiation is completed. So this test bench is actually taking the DUT and applying these signals, but these signals right now does not have any values, right? So I need to provide conditions and values right here. So for that I need to have initial block. Okay, so now we will manipulate the input signals and observe the output signals, right? So just manipulating the input signals, you go into the initial block and write the signal values. So I will be starting with writing A is equal to 0 and B is equal to 0, both the zeros, and I will observe those values. Now for observing the values we will require some time, right? So I will just add a delay. This is how you add a delay in here. Just write a hash and just give the delay. I'm writing a 10 nanosecond delay here. Now I am saying 10 nanosecond delay. How is the unit defined? If you go into the top of the file, you can see this line. Now time scale 1 nanosecond and 1 picosecond. What does this mean? This 1 nanosecond is basically the unit of time. Whatever I write after the hash mark is the unit. It takes the nanosecond unit. In the right side you can see 1 picoseconds as well. This is the precision of the time. Okay, so if I write something like 1.333 nanosecond, this will be taken like nothing will be truncated here, and it will be taken like this only, because the precision limit is 1 picosecond, right? And 1 picosecond is 10 to the power minus 3 nanoseconds. So we can take three fractional values, so this can be represented, right? If I go anything beyond this, this all things will be truncated. Okay, to include all these things you need to increase the precision again. So I have to go from picosecond to lesser than a picosecond, right? So this is how the timing is, units are set, and you just manipulate the signals. So I will manipulate the signals. I have written 0 0. I'll write all the possible signals, right? Okay, so as you can see, I've written all the possible signal values. And now the question you might have, like a doubt you might raise, is that when we have a large amounts of input and output ports, let's say 4 or 5 input ports, do we write all these signal combinations? And that is a question that will encounter like in the next in videos 20 to 30 or something, because there we will have a lots of signals. In verification, this is called Testbench verification, right? In verification department you have system Verilog, and you have universal verification methodologies and all those things. So system Verilog provides lots of other concepts such as classes and object oriented programming concepts, right? There you can use random functions and everything, where randomly the inputs will be allotted and it will be tested. Go into run simulation, just go into run simulation, run behavioral simulation, click this zoom fit option, and here as you can see when the input A is 0 and B is 0, your output is 0, right, in AND gate. And when the input is A is 0 and B is 1, the output is still 0. The input is A is 1 and B is 0, output is still 0. And when both are 1, right, the output is 1, right? Now this has been simulated for a large amount of time, and here's the reason why. We did not actually finish the simulation, so this simulation goes on continuously. So we have to add this thing here. After you are done simulating, you have to write a system command. Now system commands begin with $sign. Okay, what is the system command? System commands is all the control based commands here. So just write say system command $stop, and here just save it and relaunch the simulation like this. And now if you go into the simulation and zoom fit it, you see after we check 1 1, the simulation is automatically stopped. You have to add a stop after you are done simulating, you need to stop the simulation. Okay, now let's move on to implementing this on FPGA. So here for implementing this on FPGA, you just need to generate the bit stream. Okay, here you can see I have the FPGA and I'll just program everything here. First two switches were the for A and B, and this LED is the output. So as you can see, if I these initially are 0 0 0 1 1 0, and when I do 1 1, this LED glows. So AND gate is actually implemented on the FPGA. Now we will implement all the other gates. So what I'm going to do is, in a single module I will implement all these gates. I will define multiple outputs. So I will define y underscore AND. So in a single module I have defined all the outputs, and I'm going to assign all the outputs. So in the NOT gate you only have single input, so let's take input as the first one. Let's go with AND NOT of A. Okay, so I've written all the expressions for all the logic gates in different outputs, and now we have to make the changes in the test bench as well. Okay, so now I've defined I've connected all the new outputs with the DUT outputs, and now the signal manipulation is going to be the same because the inputs are the same, right? Let's run simulation now and run behavioral simulation. Now you can see different outputs related to different logic gates, right? So if you see the AND gate, it's still all zeros until both of them are 1. If you go to OR gate, only it's 0 only when A and B are 0, otherwise it is 1. NOT gate, if you can see, in the NOT gate we had put NOT of A, right, because it's a single input. So when the A is 0, NOT of A is 1, and when A is 1, NOT of A is 0. And in the NAND gate you only have 0 when both of the A and B are 1. In the XOR gate, when the inputs are 1 0 or 0 1, they are 1, otherwise they are 0 at both 1 1 and 1 0 of A and B. And XNOR, it's the exact opposite of XOR. Now if you run synthesis and generate the circuit, we'll see an interesting thing over here. Let's see if you can notice it. If I open the schematic that synthesis tool has generated, okay, let's see the schematic in the RTL analysis first, because there you will be able to see the gates clearly instead of LUTs. So here, as you can see, this is a generated schematic, but there is an interesting thing over here. See if you can notice. Just pause the video and notice. So the interesting thing that has happened here is we had NAND and NOR, right? NAND gate and AND gate. So as you can see, NAND output is simply has taken the output from AND and has inverted it, right? In the XOR output, XNOR output, it has taken the input from XOR output and just inverted it and given it as XNOR output. So what is this? This is optimization, because in the code, if you remember, we have written single expressions. We haven't written y NAND is equal to NOT of y AND, right? We haven't written that. So this thing is pretty powerful. Vivado synthesis tool has itself done a optimization inside the generated circuit, right? So this is very powerful thing. So the synthesis tool not only generates the schematic, it also generates an optimized circuit, right? It optimizes the things, data paths. This is what I wanted to emphasize. Okay, so as you can see, the bit stream has been generated. Let's put it on the FPGA and see whether it's working or not. To program the FPGA. So here's my FPGA, and right away, as you can see, both of them are 0, and this series is from AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate, and XNOR gate. So you can verify. I will move this. This is 0 1. This is 1 0, and this is 1 1. Okay, so now we have verified all the logic gates on the FPGA. This was the day 2. So we have finished all the test bench verification as well, and all the we have implemented all the logic gates on the FPGA and saw it working on the FPGA. Join me on day 3, where we are going to be interfacing the FPGA with Arduino or ESP32 boards, like such boards. Now, how we'll pass the information from one board to another board. And it's very important to understand that the only input methods are not buttons. We have other input and output methods that we are going to see tomorrow. We will drive all this logic not using switch but using another microcontroller board. So let's say that will be interesting. Join me on the next video. Thanks for watching.